Hey everyone, in this video lecture we'll be discussing sections 9.3 and 11.3. I'm going to do things a little differently this time. I'm just going to do a voiceover with the PowerPoint and do the example simultaneously in one video. That way we can save some space on the disk in MATLAB and Blackboard. So section 9.3 deals with hypothesis testing for population proportions. So in 9.1 and 9.2, we saw two separate tests for the population mean. That was when sigma was given and when it was not given. Here we're going to be dealing with a hypothesis test for the population proportion instead of the population mean. So the procedure for hypothesis testing for a population proportion is exactly the same as that for the population means. The only difference is with calculating certain test statistics and things like that. Okay? So recall that the standard deviation from the sampling distribution for proportion was given as sigma equals the square root of p times q over n. And q is 1 minus p. So that is our standard deviation for the sampling distribution. And we calculate a z-score in the following way. Z is equal to p hat minus p divided by that standard deviation. So the process for testing this hypothesis, any hypothesis here, is similar, just the formulas kind of change a little bit. There are some test conditions for this one proportion z-test. Recall that from chapter 7 we found the sampling distribution for a population proportion, or for these sample proportions, was normal if two things happen. Of course, we need to take our samples randomly and independently of one another, and our sample size condition here, NP is greater than or equal to 5, and NQ must be greater than or equal to 5. So of course we would want to check that before we start our hypothesis test. Alright, so let's just get into it. So we want to do a hypothesis test for population proportion here. So example 1 says, suppose the national unemployment rate is 3.5%. In a survey of 450 people in a rural Wisconsin county, 22 are found to be unemployed. County officials apply for state aid based on the claim that the local unemployment rate is higher than the national average. Test this claim at the 0.05% significance level. All right, so first things first, we need to state our hypotheses. So one, hypotheses. So note that our null and alternative hypothesis are going to be slightly different this time, because what variable are we doing the hypothesis test for? And that is the population proportion. So we're not going to put mu here, we're going to put p. This is the parameter of interest for our problem. Okay? So here, if we kind of deduce what these are going to be, remember the null hypothesis is always equal. And we'll get the sign for the alternative hypothesis based on our problem. So here it says, suppose the national unemployment rate is 3.5%. The county officials apply for state aid based on the claim that the local unemployment rate is higher than the national average. So here our 3.5% is our P. So we'll put 0.035. That's 3.5%. And we're testing the claim to see if that is the actual unemployment rate here is higher than 3.5%. Okay. So we have our null and alternative hypotheses. This is a, notice that this is a one-tailed test. One-tailed test to the right. Okay. 2, we need to find our test statistic. All right, so the formula on one of the previous slides was p hat minus p over the square root of pq over n. All right, so we need to generate a few values here. So we need our p hat. We have p. We can find q. We just need, and we have n here. So what is our p hat? Remember, p hat represents the sample proportion here. So how do we get that? So know that p hat is calculated by doing the number of successes r over n. So here r represents the number of people who are unemployed. So that would be 22 out of the total 450. That's the proportion, the sample proportion of people that are unemployed. So let's calculate that. 22 over 450 is 0.049. Okay. So we can see that from our sample, this value is higher than the national average, but is it significantly higher? Okay. So let's plug in our values. 0.049 minus 0.035 over square root 0.035 times 1 minus that is 0.965 over 450. So let's figure out what that is. Getting 1.62. So our test statistic is 1.62. Step 3, recall, is finding the p-value for our test. P-value represents the probability of getting a sample like this under the null hypothesis. So here what we can do is, let's draw our distribution. Remember, we are using the z distribution here for proportions. And we have 1.62 as our test statistic, so that's over here. And we're looking for the area to the right, the probability that it's greater than that. So our p-value is inverse norm. 1.62 to 10 to the 99, 0, 1. Excuse me, normal CDF. We're finding a probability here. Normal CDF. 1.62, 10 to the 99, 0, 1. So our p-value is 0.0526. Lastly, our conclusion. So let's go back and see what our alpha level was. Here it says test the claim at the 0.05 significance level. So we can see here with alpha equal to 0.05. How does our p-value compare to that? Well, it's slightly larger, right? P is greater than alpha. Thus, what do when it's bigger? We reject, right? We reject the null hypothesis. we retain the null hypothesis. Retain the null hypothesis when it's larger. There is not significant evidence to support that the unemployment rate is higher than the national average. Retain. Right. So you can see the process is exactly the same. The only difference is a couple of formulas that we're using. Just keep in mind that with proportions we always use the z distribution. There's no case where sigma is known and unknown like we did with means. So we always use the z distribution for this type of problem. All right, let's try another one. Sample 2. All right, so it says a random sample of 750 people is selected, of whom 92 are left-handed. Use these sample data to test the claim that 10% of the population is left-handed. Okay. Let's see what we can do here. We want to write the null and alternative hypotheses. All right. One. Hypotheses. All right, so here we have 750, 92 are left-handed. That's how we'll find p hat. Here we're testing the claim to see, to test the claim that 10% of the population is left-handed. So here 10% represents our population proportion. So this is what we're testing against. So our null hypothesis is that p is exactly equal to 0.10. And our alternative hypothesis, let's think about this one. What would the sign be in between? Well, here we're trying to test the claim that the 10% of the population is left-handed. So it doesn't really give us a direction. So let's use the not equal to symbol here. So this is a two-tailed test this time. Okay, two-tailed test. Step 2, test statistic. So recall z is equal to p hat minus p over pq over n, square root. So we have our p, we have, we'll be able to find q then, we have n, we would just need p hat. And recall p hat comes from the problem. Here, 92 out of the 750 were left-handed. So p hat is simply 92 over 750, which is 0.123. Alright, so let's plug in our values. So 0.123 minus 0.10 over the square root. 0.10 times q would be 0.90 over 750. Calculating that, we will get about 2.07. Step 3 is find the p-value. We're working with normal distribution, z distribution. .07's up here, so we need this area. But recall that this is a two-tailed test, right? This is a two-tailed test, so we need to check above and below the positive and negative test statistic. So we're looking for these two equivalent areas. So our p-value is 2 times normal CDF. And we can find either of the two. It doesn't really matter. So let's do the upper area. 2.07, 10 to the 99, 0. Let's see what that gives us. Right, after multiplying by 2, we get 0.0385. And lastly, our conclusion. The problem did not give us alpha, so we'll just assume it's 0.05 again, with alpha equal to 0.05. How does the p-value compare to alpha? It is smaller than alpha. P is less than alpha, so we reject the null hypothesis. There is significant evidence to support the claim that the proportion of lefties is different from 0.10. So we're not concluding higher or lower, just different from here. Okay. All right, so that's how we test a proportion. You can see it's very, very similar. Just be sure that you are using the appropriate parameter here and the appropriate formula for your test statistic. All right, so that does it for 9.3. Let's look at 11.3. So in chapter 9, we dealt with testing hypotheses for the population mean and the population proportion, which we've just done. There's one more parameter that we have yet to test, and that is the variance or standard deviation. Recall that the variance and standard deviation were measures of spread. So here we're going to look at determining whether our sample data is more significantly spread out than the population data. So when we test sigma squared, that's our variance, right? So sigma squared, that's a variance. We have a normal population with variance sigma squared and a simple random sample of n measurements. Then the sample variance s squared. Then we have this test statistic here. So there's a new variable. This is called the chi-square variable. And we calculate the test statistic using this little formula here. So it's n minus 1 times the sample standard deviation squared over the population variance. So again, this is coming from a different distribution, a new distribution called this chi-square distribution. This guy also uses degrees of freedom, and they are the same as our t distribution, n minus 1. So the process of, so here's an example of the chi-square distribution. So you can see the chi-square distribution is skewed to the right. It's no longer normal. So here we'll be finding areas to the right or to the left or a two-tailed area as we did with our other ones. We'll just use our calculator to get it. This will be finding the p-value. Okay. So the process for testing the variance is almost exactly the same as testing for mean or proportion. We follow that same four-step process. It's just the formulas get a little bit different. So let's try this example. Right, so it says for years, a large discount store has used independent lines to check out customers. Historically, the standard deviation of wait times in line is 7 minutes, and the manager tried a new single line procedure. A random sample of 25 customers using the single line was monitored, and it was found that the standard deviation of this sample was s equal to 5. Use alpha at the 0.05 level to test the claim that the wait time is reduced using the new procedure. Okay? So, here's section 11.3. Example 1. First thing we need are our hypotheses. Right? So here, if you notice, it is giving us information revolving around standard deviations and no mention of any means or proportions are being given. So this kind of indicates to us that we should be using this type of test, right? So let's see, our null hypothesis, alternative hypothesis. We are testing for a population variance here, sigma squared. For our null hypothesis, this is always equal to. So what is the population variance here? Well, we know that historically the standard deviation of wait times in line is 7 minutes. So that's our standard deviation. That's sigma, right? So they're giving us sigma is 7. So what would be sigma squared? Sigma squared would be 49. Our alternative hypothesis is the claim that we want to test. So if we go down to the last sentence here, so at this level of alpha level, we want to test the claim that wait time is reduced using that new procedure. So we want to test to the left. Is sigma squared less than 49? Next up is our test statistic. So we just use our formula from the previous slide. This guy right here. Let's write that down. So chi-square is n minus 1 s squared over sigma squared. Okay. So let's just plug in our values. So what is n? Here we have a random sample of 25. So that would be 25 minus 1 times our standard deviation squared, which is 5 squared, over sigma squared, which we said was 49. We'll just write 7 squared there. That's fine. So let's calculate that. 24 times 25 divided by 49. So here we're getting 12.24. Okay. Next we need to find our, so here are our hypotheses and test statistic. To find our p-value, we need to use our calculator to get it. It's a little bit of a different process in the calculator here because we're using a different distribution. So what we're trying to do, here is our chi-square distribution. It's right skewed. Okay. Now, if we look back, the chi-square distribution actually starts at 0 here. So 0 is all the way at the left-hand side here. So 12.24 maybe is up here somewhere. And we are looking for the area to the left of that value. So it looks like our p-value is going to be pretty large this time. So how do we get it? So p is equal to, if we go into our calculator, go to second distribution, and you can see in option number 8, we have chi-square CDF, all right? Chi-square CDF. So let's see what we need for our parameters for that. So our lower is going to be 0 always. Our upper is going to be our test statistic, so that would be 12.24. We also need our degrees of freedom. That is always n minus 1, so that was 24. Paste it in there. Right, so we get 0.0229. So not quite as big as we thought. All right. We are testing at the 0.05 level. So our conclusion, with alpha equal to 0.05, p is less than alpha. So when the p-value is small, there's not a good chance to produce samples like we did under the null hypothesis. It gives us evidence in support of our claim. So we reject the null hypothesis. There is significant evidence to support what? Well, let's go back to our stem. What were we testing? We went to test the claim that the wait time is reduced using the new procedure. So there's evidence to support that the wait time is reduced using the new procedure. That's it. You can see that the process is exactly the same. The only thing that changes are what we're testing for and our test statistic. Okay. Oh, again, this was chi-square CDF 0 to 12.24, 24. Okay. Let's do one more. Two. All right, so it says let x be a random variable that represents weight loss after a specific diet for 6 months. It is found that x has a normal distribution with sigma equal to 5.7 pounds. A new modification to the diet has been implemented. A sample of 21 people used the modified diet for 6 months. The sample standard deviation is 4.1 pounds. Using the 0.01 level, does this result indicate that the variance of weight loss is different from the modified diet? All right. So let's get our hypotheses going. So identify the problem that we're doing. So is this a mean, a proportion, or something involving the variance? Well, here we're given all the information about standard deviations, so we're testing a variance. Always equal for our null hypothesis. So what is the population variance equal to? Well, the population standard deviation is 5.7. So our population variance is just that value squared. 5.7 squared is 32.49. Okay. So here, 32.49. All right, now which direction are we testing? So let's look. using the alpha equal to 0.01, does this result indicate that the variance weight loss is different from the modified diet? So here we're just testing for a difference, which means we'll use the not equal to symbol. It doesn't specify greater or less, it just says different, so we use the not equal to symbol there. 2, our test statistic. Recall this uses the chi-square distribution. Was n, its test statistic was n minus 1 s squared over sigma squared. So we have a sample of 21 minus 1. Sample standard deviation was 4.1 squared over 5.7 squared. Let's see what we get. So here I'm getting 10.35. Next up, our p-value. Let's draw a distribution where this is chi-square, so it's a skewed right distribution with 0 at one end. So 10.35 is here. We're looking for this area. So our p-value is chi-square CDF, 0 to 10.35, with how many degrees of freedom? 20. So again, we're going second distribution, down to chi-square CDF. Put our new test stat in there. And our degrees of freedom. So we're getting 0.0386. But remember, this is a two-tailed test, right? This is a two-tailed test. So we need to multiply by 2. So multiplying by 2 gives us 0.0773. So our conclusion, with alpha equal to 0.01, p-value is larger than alpha, so we retain the null hypothesis. There is not significant evidence to support that weight loss was different on the modified diet. Right. So once again, process is similar. Watch out for that not equal to. We need to multiply our p-value by 2 once we find out. Okay. Alright, so that does it for 11.3. Now I just want to quickly run through some problems in identifying the type of problem that we're given. Okay. So, which test do you use here? So here, this exercise we're going to go through, we're going to read a question, and we're not going to perform the test, but we're going to identify what type of test it is. And if the test should be used, that means does it pass the normality conditions or sample size or population distribution. We'll identify if it's a one-tailed test to the right, a one-tailed test to the left, or a two-tailed test. And we'll identify which test statistic we should use, or from which distribution we should be checking. Okay. So let's look. Here's one. So Pyramid Lake is on the Paiute Indian Reservation in Nevada. Suppose a friend tells you that the average length of trout caught in that lake is 19 inches. A random sample of 51 fish caught yields a sample mean of 18.5. The estimated sample standard deviation is 3.2. Does the data indicate that the average length of trout in the river is less than 19 inches? Okay. So, A. All right, so based on the information that's given, which test should we be using? Well, notice that we're talking about averages, right? The average length of trout is given. We want to test to see if the average length of trout is less than 19, right? So which test should we be using? This is a test for a mean. Right? Are the conditions met? This means can we assume that the sampling distribution of X bar is normal? Well, we need to know one of two things. We have to be able to tell if the sample size is greater than 30 or if the population is normally distributed. So do we see any of those conditions? So here we have a random sample of 51 fish. Say yes, n is greater than 30. 3, is this a one-tail or two-tailed test? In which direction? All right, so this comes from our alternative hypothesis. So if we go through, what are we trying to test? Does the data indicate that the average length is less than 19 inches? So this is a one-tailed test. To the left, less than, right? And which distribution should we use? So should we use Z, T, or chi-square? Well, recall that to determine that, we need to know for the test for the mean is if sigma is known. Is sigma known here? Well, let's go through it. We know that the population average is 19, the sample mean is 18.5, and the sample standard deviation is 3.2. So we do not know sigma. So sigma is unknown. We use the student T distribution. Okay. Next. It says before 1918, the proportion of female wolves in the Southwest was 50%. However, cattle ranchers started efforts to eliminate wolves to protect their herds. In a recent random sample of 34 wolves, there were only 10 females. Does the data indicate that there is a reduction in the female wolf population in the region? All right, so which test should we use? Does this test for a mean, a proportion, or a variance? Well, here we're given percentages, so that's a big indicator that this is a test for proportions, test for P, population proportion. Are the conditions met for the normal conditions? Well, let's see. Remember that we need n times p to be greater than 5 and n times q to be greater than 5. So what is n times p? Well, P here is 50%, N is 34. What is 34 times 0.5? Is that greater than 5? Yes. It's N times Q. Well, what's Q? 0.5 also. Is that greater than 5? Yes. Yes, the conditions are met. This is a one- or two-tailed test. So what are we testing for? Does the data indicate that there is a reduction in the female wolf population? So we're testing to the left. This is a one-tailed test. To the left. Again. And which distribution should we use? Well, test for proportions, always use Z. No matter what. See? Right. 2, 3, 4. Right, so let X be normally distributed, where X is the age and years of rural Quebec women at the time of her marriage. In 1941, the population variance was 5.1. Suppose a recent study was conducted for 25 of these women, and it was found that the sample variance was 3.3. Is the current variance different from that in 1941? So which test? Well, this one's easy. It says everything about variances, right? So this is a test for variance, single square. Are the conditions met? Well, what were the conditions for that test? Let's go back a little bit. So the only condition that we need is if we have a normal population. So we need to know if the population is normally distributed. Is that the case? Is X normally distributed? Yeah, it is. Okay. Yes, X is normal. This is a one- or two-tailed test. So let's go to see what we're testing. Is the current variance different from 1941? So it doesn't indicate a direction, so this is a two-tailed test. Remember, we would need to multiply the p-value if we were finding it by 2. And which distribution is used? Well, recall variance used chi-square. One more. A random sample of 25 values is drawn from a mound-shaped symmetrical distribution. The sample mean is 10, and the population standard deviation is 2. Does the data suggest that the true population average is greater than 9? So which test? Are we testing for an average, or a population mean, population proportion, or population variance? Well, here we're testing for population average, right? So it's a test for mu. Are the conditions met? So recall the conditions for a test on the mean. We either have to have a normal population or the sample size is bigger than 30. So here we have a random sample of 25, so that's not bigger than 30. But the values are drawn from a mound-shaped symmetrical distribution. So this tells us that that distribution is normal. Mound-shaped symmetrical is just another way to say normal. Yes. The population is normal. Is it a one- or two-tailed test? Let's go and see. Does the data suggest that the true population average is greater than 9? So this is a one-tailed test. To the right this time. Greater than, right? Lastly, which distribution should we use? Well, it's either z or t. It depends on whether we know sigma. Do we know sigma? Well, the sample mean is 10, and the population standard deviation is 2. That tells us sigma right there, right? Population standard deviation is sigma. So that is known. Sigma is known. So we use sigma. Alright, so that does it for this lecture. You can go ahead and start your WebAssign homework.